Have you ever wondered what we could learn if the world around us could talk? I mean, what if a bridge could tell us it was feeling stressed, or a pipeline could shout, "Hey, I've got a leak right here"? It really sounds like something out of science fiction, right? But this is exactly what's happening, all thanks to a technology you probably use every single day, the humble fiber optic cable. So how does this tiny thread of glass get a superpower for sensing the world? Well, let's dive.
Okay, so we usually think of fiber optics as the backbone of our internet, just shooting data around at the speed of light. But that exact same thread of glass can be turned into one of the most sensitive sensors ever made. And we're talking sensitive enough to work in some of the most extreme and demanding places you can imagine.
For instance, take a look at this. Deep, deep in the ocean, silence is everything. For a nuclear submarine, being able to detect another ship without being detected yourself, that's the whole game. And the tool they're using isn't some crazy electronic gadget. It's arrays of fiber optic cables that act as these ultra-sensitive underwater microphones, basically letting the submarine hear with light.
Which brings us to the big question, right? How on earth can a simple piece of glass, literally thinner than one of your hairs, hear a ship miles away in the deep ocean? The answer, it turns out, is both incredibly elegant and just brilliant.
So to understand this, we've got to look at how light traveling down that fiber can be made to react to the world outside of it. Yeah, it's a little bit of physics, but I promise it's really, really cool.
So the fundamental idea is right here. A fiber optic sensor works because some force from the environment, like the pressure from a sound wave, or the strain on a wing, or a change in temperature, that force physically changes the light that's passing through the fiber. Our job is just to measure that tiny change. So how in the world do you measure such a tiny change? Well, one of the classic methods is something called interferometry. You start with one beam of light and you split it in two. One half goes down the sensing fiber, which is out there in the environment. The other half goes down a protected reference fiber. Then you bring them back together. If anything disturbed that sensing fiber, even a sound wave stretching it by a microscopic amount, it creates a detectable pattern. It's an incredibly precise way to see the invisible.
But there's an even more direct, even more ingenious way to do this. Instead of comparing two different fibers, what if you could build the sensor directly inside a single fiber?
Well, that's exactly what a fiber Bragg grating does.
Using UV light, scientists can actually etch this tiny, invisible pattern right into the core of the glass. The best way to picture this Bragg grating is to think of it as a series of microscopic mirrors, all spaced perfectly apart. Now, because of that perfect spacing, these little mirrors are tuned to reflect only one very, very specific color or wavelength of light. Everything else just passes right through. But here's the key. If you stretch that fiber, or you heat it up, you physically change the distance between those mirrors. And this is the magic moment. When you change the spacing of the mirrors, you change the color of the light that gets reflected back. It's kind of like tightening a guitar string. The more tension you add, the higher the pitch of the note. For the fiber, the more strain it's under, the more the color of the reflected light shifts. It's that direct.
So, let's just walk through that one more time. Step 1, a sound wave puts strain on the fiber. Step 2, that strain changes the mirror spacing in that Bragg grating. Step 3, this changes the specific color of light that gets bounced back. And finally, Step 4, a detector just reads that changing color, instantly turning it into a super precise measurement. It's just an incredibly simple and tough way to sense the world.
Okay, so now that we get the principle, let's look at where this incredible tech is actually being used. And believe me, it is showing up everywhere, especially in industries where you need absolute precision and reliability.
In the world of high-tech manufacturing, these tiny sensors are a total game changer. They give robotic arms the pinpoint accuracy they need, and they're used to make semiconductors, where being off by even a fraction of a hair can ruin a whole batch of computer chips.
And in really fast-paced factories, they're like the ultimate quality control inspectors. They can spot tiny marks on packaging that's flying by or check the fill level in clear bottles, jobs that are just way too fast or too subtle for a person to do.
And what I think is just brilliant is how this scales up. You can go from the microscopic world of computer chips to the absolutely massive. A single fiber optic cable can run along a pipeline for hundreds of kilometers, detecting the tiny temperature drop from a leak or the vibrations from somebody digging where they shouldn't be, and send that info back instantly.
And honestly, the list just goes on and on. They're used for counting pills, guiding super thin plastic films, spotting nearly invisible glass objects on a conveyor, and because they're passive, meaning there's no electricity right at the sensor, they're perfectly safe to use in hazardous and even explosive places.
So this all points to a much bigger idea. This isn't just about making factories work a little better. It's about making our entire world more intelligent, more self-aware.
So why choose fiber over something else? This really sums it up. First, they're totally immune to electrical noise. They're so small you can bake them right into concrete or airplane wings. They're incredibly tough. They work in extreme heat and cold. And because they're passive, with no electricity at the sensing spot, they're super safe and reliable.
And when you put all those advantages together, you get this, the idea of smart structures. Imagine bridges, buildings, dams, all with a nervous system built right in. A whole network of these fiber sensors constantly monitoring the health of the structure, reporting stress or tiny cracks long before they could ever become a disaster.
And one of their most powerful features is just how stable they are. As this quote points out, you can measure the strain on a bridge today, come back years later, and compare the new data to that original rock-solid baseline. That's something that's almost impossible to do with traditional electronic sensors, which tend to drift over time. Which brings us right back to where we started. We are literally giving our world a voice. From the deepest parts of the ocean to our tallest skyscrapers, these little threads of light are becoming our planet's nervous system. And it just leaves you with this amazing thought. If our world could really tell us how it's feeling, what do you think we'll learn?
Let's study more and like, share, and subscribe for such more content and comment something you want to learn.